Okay, so we have done semi-synchronous and synchronous consistency, and now we can do a little bit more. So can we do nested transactions now? Travelocity, I have to check with Hilton, I have to check with American Airlines. I need to check. Okay. If I'm the only proposer, sorry? All synchronous. What, you know, so I can do that now. Okay. For master slave backup, you know, if I go and look at these systems, some of them say we want asynchronous, sometimes some say semi-synchronous, some say synchronous, but now we can do them all. Okay? And that brings us to the problem that you guys really wanted to address, which is what happens here, right? And the answer you guys kind of know, or what we can easily guess, is to have a coordinating guy. So you send the request, sure enough, but this guy has to echo your request back for it to be really heard. Okay? So the remote guy, there's one proposing general. One coordinating general. There can be multiple proposing generals. So we go from a synchronous system like this, where each proposer was sending data directly, to a centralized synchronous system where all proposers send to one proposer, which goes and sends the data out. Okay? And this is the case when we have centralized synchronous. We can also have centralized asynchronous, where again, we don't want any feedback, we just want synchrony, and we go and just learn through this guy so that we serialize things. Okay, yeah.
In this case, if there's two proposals coming in, and say one is like just right before, would the second one get rejected, or would it wait for the first one to complete?
Okay, so the question now becomes, what if there are two pending proposals? A second proposal comes in while the first proposal is still pending, right? That's your question? Mm-hmm. Okay, let's quickly just go through this, and we'll have to address this next time. But the way this works is you propose, becomes pending, you remote propose now, remote propose, before you remote propose, somebody else might have remote proposed, so that also made it pending, and that, so you proposed, there was a remote propose, before your remote propose could be executed, somebody else proposed, the local guy could have proposed, for instance, they resulted in a remote propose, and now the first learn might happen, so, and then the second learn might happen. And in this case, I allowed the second proposal to go through, even though when it was processed, I had a pending proposal. Okay? And in the synchronous centralized case, the same situation, except that I send the accepts across. Okay? But again, I'm sending the accepts across, even though the first proposal is pending. One proposal is pending. So should second proposal be accepted is the question that you asked and that I asked back here, which we'll have to wait for, whose answer we'll have to wait for. Okay? Oh, no. That hash code tape question was to do the assignment. No. The question that Brennan asked last time was that if we have a remote proposer, so a centralized proposer, and a proposal is pending, and before it gets resolved, another proposal comes in, what should we do with the proposal? Right? And so what do you guys think? What should be done? Or what? Oh, hang on, I haven't. Let me go and switch on the projector. Okay, so the question is, what should we do? Right? And one answer is, don't do anything. In other words, just let commands execute in the order they're supposed to be executing. So I guess I'm going beyond the centralized process. I'm just saying, let's think in general, two clients are trying to execute commands concurrently. Okay? And the question is, what should we do? And one answer is that we just let the commands come in whatever order they come in and execute them and that order at each site. So each site executes its command, then sends it to the other site. And we have C1 and C2 at one site, C2, C1 another site. So this is a non-atomic broadcast that you guys have been doing, right, for your commands especially. And it's efficient. It's going to be the fastest among all the ones that we will see. So where can this fail? They're not commuting, right? So if you take a hash table, can you think of two commands? So firstly, where can it succeed? Take a hash table.
It just happened to, like when you do a get and a remove at the same time. If the get happens to be executed before the remove, you will get something and you remove it timely. But if it happened in the opposite order, you basically messed up.
Okay, so you're telling me when it won't work. If you have one command that reads another command that deletes.
Yeah, if you have two gets.
Right. So that's when it won't work. So when will it work? Take a hash table example. Yeah.
Two puts, maybe?
Two puts.
Or no, I guess if they have the same thing.
No, keep going. Two puts.
Two puts with different keys.
With different keys.
Yeah.
Okay. So we have put K1, V1, K2, V2. Okay. So how can we improve on this? We saw the atomic execution. So what you do is now you need a central guy to mediate. Okay. So and we could this is where it fails. If you use the same key, it will fail. So what could we do to make this situation work? We could just order commands. Okay, that's what you were doing with atomic broadcast. You send it to the server echoed it back, and you executed commands in the order in which the echo occurred. Right? And this works. This example works, and now we can take Nick's example where it won't work. Right? One guy puts, the other guy removes, deletes, and if the object has been well, in a hash table, if the delete is expecting, what I was trying to say was that there was already a key. Okay, what I'm trying to say is that there's a key and I delete it. Okay, so it's considered a file in a directory. So I have deleted a file and you modified it. That's what I'm really trying to think here. So now, if I delete the file first and then you try to modify it, your modifier won't work. As it turns out, in the hash table, it'll just put a new value. And that's pretty much what a lot of synchronization systems will do. But in general, that can create a problem because what you're referencing has gone away. Okay, you're trying to change the color of an object that's deleted. So what should we change? Nothing to change. Okay, we don't want to create a new object at that point. So we've got non-atomic and atomic. What adjective should we use? So what should we do in this situation, by the way, when there's a command like this, which we consider as conflicting? Okay, and in your simulation it is move and take, right? So, sorry? Sorry?
You have to serialize it.
So you want, yeah, Brennan?
I was going to say, like a one that won't fail but isn't like ideal would just be ignore one of them.
One that won't work, won't fail, but may not be ideal is to ignore one of them. Mm-hmm. And when we ignore a command in databases, what is it called? Abort. Okay. So this is a term I'm using from databases. So the adjective I will use for this kind of concurrency control would be, if you study databases,
Aborted transactions.
Aborted transactions are done to ensure some quality about transactions. So you guys know about the ACID properties, right? What is the I there? What does I mean? Isolation. And how do you, and isolation, what is the correctness criteria for isolation? What is the, so what does isolation mean? It's not that they are totally isolated, right? They're sharing a database. So to guarantee isolation, you have to guarantee some quality about transaction processing. And it's a term that you will hear again and again and again. Serializability? Okay. So we'll make the transaction serializable, where, you know, aborting is fine. Okay? It may not be fine if you work in collaborative systems like I do. You know, one guy's edited a program and another person's edited a program for 3 days, you can't abort one of them. Okay? So when there are long-lived transactions, you don't do that. We try to merge things. Okay? But here we are not talking about merging. We are not. We're assuming we know nothing about the objects being manipulated. So in fact, that's an important point here, that the concurrency control here is type independent. We don't really know what's inside the object. Okay, but in fact, if we could know something about hash table or about directories that I mentioned, then we could do a better job than something that just blindly does the same thing for all operations. Okay? But what we can do is define some parameters, and each application can decide whether it wants non-atomic, atomic, or serializable. Okay? So the consensus system that we built so far will allow all three now. Okay? Because we now have a central guy also. We can ensure serializable, we can ensure atomic, and we can just assume that there's no echoing back, and we just the centralizer is just a mediator. Okay? So we are seeing now advantage of the central guy. Okay? So let's go and see how the central process is implemented, and you know, you've all done it, so that's why I'm going a little quickly over this. So now that we have a mechanism that's centralizable, that doesn't mean we will centralize. Okay, we've got something fancier, so we can always support something that's less sophisticated. Okay, so we'll have an option saying, do you want to run in the centralized mode or not? And if it's not centralized, we will just run our regular local propose. Okay, and the local propose can be synchronous or asynchronous. In my implementation, this is a subclass of synchronous. Synchronous itself goes and checks if you really want synchronous, otherwise it goes to asynchronous, which is this superclass. So we've got this flexibility. Okay, and if it's centralized, then we send the propose request to the central guy, which may be us. Okay, so all members are equal here, and there we go and check if we're supposed to be serializable or not. If we're supposed to be serializer, we go and check if there's some pending proposal that we know about. And if so, we go and say, oh, we've got a fault now, it's concurrency conflict. This is a fault that the consensus mechanism is putting in. It's not something that an application detects. And otherwise, we do a local propose, essentially. Okay, because we are now the server, and we've got a call from somewhere. Okay, and we just do a regular local propose that was happening in the synchronous case. And the synchronous case, again, looks at local propose, looks at the parameter and decides whether the local propose should go up to its superclass or it should do the synchronous propose. Okay, so pretty straightforward. Okay, questions? Okay, so let's just go and see this working. You can see now my screen has become much bigger. Okay, so the central person means bottleneck, right? You see the bottleneck in the number of lines now I suddenly have on a screen. Okay, with the same stuff that I had before, with the same two proposals being made. So what happens? This is a server, and he's also a proposer. So he goes and sends a remote propose request to itself. Okay, and that is then received. Okay, and in the meantime, another remote propose arrives from proposer 2. Okay, and since this proposal has not been resolved, we send back a concurrency conflict message. Okay, to the proposer. And in the meantime, our own proposal gets all the acceptances that we expected. You know, we remember we were counting the acceptances, so we count the acceptances, and when we get enough, we go and declare success. So the central guy declares success and broadcasts the success to everybody else. Okay, in the synchronous system, the proposer did that, and we assumed there was only one proposer. Now we allow multiple proposers, but the central guy goes and takes this request and sends it to everybody else. including the original proposers. Okay? And they learn what the new value is. So we're just seeing the algorithm that I talked about in motion here. Okay? And can you guys see what's happening below this line? So we reach a consensus of 42, and yet there's more activity after that. If you guys remember, my proposals were done in a loop. And that loop basically checked if it got a concurrency conflict, it went and reproposed, which we said was not consistent with serializable transactions. But it's something that a lot of works assume happens. Okay? So that's what's happening. Now this particular proposal has been resolved. So the new proposal that is reissued by proposer 2 will not get a concurrency conflict. Okay? But because our vetoer, we've also got a vetoer there. Or we also got a vetoer in the application, and one of those applications rejects the value and says, I don't like it. Okay? And so, so again, there's service denial, but this time the service denial, again, there is failure, but this time the failure is because of service denial rather than concurrency, and the loop terminates and says, okay, if my value is bad, I'll just give up and try to propose a new value, because no matter how many times I try, I'm going to get rejected. So you see the retry happening here also, and you see both cases being taken care of. One case where the proposal is pending, another case where the proposal is not pending, when a new proposal comes in. Okay?
The second time, so like it got a bunch of service denied, but it got success afterwards.
No, what's happening is the following. It's getting accepted responses from multiple sites. Some sites say success, one site says failure. Okay? So that's what's happening. Okay? So the fact is that, when there's service denial, it goes in, after the first service denial, it goes in, let me put my laser pointer on. Okay, so after the first service denial, it said, okay, I know that this is proposal service denial. And the very first denial did that. There are some pending messages that are still arriving from other sites.
Oh, okay.
That's what's happening. And by the way, you'll see this kind of interaction a lot, especially when we go to the next algorithm, that we made a decision, and yet messages are percolating in. Okay?
But in that case, we don't really care.
We don't care. So in our algorithm, this is the same centralist algorithm we had earlier. There's nothing new here. We've just centralized it. Even in the centralist algorithm, this happened. And if you remember, in the algorithm, we said that when a new response comes in, and if it's not pending, we just don't do anything. Okay? So this is now the second request, and we have a service denial, and that's it. And here's a rejected proposer. It goes and gets sends this proposal, it gets a concurrent operation, and it goes and sends a new proposal after that with a new ID. The same value with a new ID, and this time it gets a service denial. Okay? So this is from the point of view of the proposer. That was the central guy. Okay? And this is your acceptor. Acceptor 3 is very nice. The glass is always half full, so it never rejects anything. And it sends a success for 42. It sends, and it sends but the number 4, that's the one that has, denied the proposal, and that's why the second round got.
The service denial is just saying that like it's a bad value.
Yeah, the checks if it's an odd number or not. I could have hardwired 42 there. So I showed you the vetoer earlier last time. That's the same code. Okay. Okay. So we've now handled the multiple proposing problem. Okay. So we've handled all cases that we were considering earlier. This was the hardest one. Okay. So I could have taken 5 extra minutes in the last lecture and finished it. So what's the big problem left? Okay, if your network is no longer reliable, then we're kind of in trouble, right? And so yes, that's one problem. So you're going towards failures. Yeah, if network is problem, you know, and we are using timeouts, so that's a solution for that. Yeah.
Your server is more than one person, so you don't have actually centralized.
No, I mean, if our server is more than one person or more than one process, then we go down, we reduce ourselves to the synchronous case that we had earlier. The whole point is we want a central, and we can get if we want it. But yeah.
If the centralized server goes down.
Centralized server goes down. If you have a leading general, you want to really protect the person, right? So, what happens when the coordinator goes away? Okay. So how bad is that? I mean, there's always this line of chain of command, right? So if one person goes, we choose another. So supposing we can do that easily, and we can, okay? Or let's assume we can for now. What's the danger? Yeah. Losing state. If we've lost all state, then it's okay. If the general, gave no orders at all, then everybody's in sync. What if the general gave 2 orders and two of the following general received it and received the order, and the other 2 following generals didn't receive it? Yeah.
So the case where you have 2 proposals, then the coordinating general goes down, and there's no one to accept or reject proposals.
Okay. So if the coordinating proposal guy goes down, and no one else comes in its place, then we certainly have a problem, because we can't coordinate any longer. I'm saying let's assume that by magic we can do that easily. The question still is that even with the new general, the problem is there are past orders that have been only partially synchronized. Yeah.
Is this where logging comes in handy?
Logging can come in handy, right?
The clients then communicate with the server using some kind of an error, kind of function, the server went down, we're going to try to reestablish state by coordinating.
Yeah, that's a very good point. The problem that's arising arises when some clients know information that other clients don't. If all clients didn't know the information, we are fine. And since the information is with the clients, we can retrieve it from the clients too. That's a key to solving the problem.
Whenever one of the clients receiving a new state, whenever they receive it, they forward it to the things close to them.
So Brennan is taking this networking course, so he's just thinking about why not, flooding is what he wanted. So he's saying, okay, we'll just do it to the ones close to us, because I'm a networking person. I don't want to go all the way to China from the US, and then they can forward it further. And in fact, when I send a message from here to 10 processes in China, the network will indeed, hopefully, especially if I do a multicast message, send only one copy to the routers that are shared, and then fork off the messages when it needs to the other routers. So yeah, so somehow the clients have to talk to each other, okay? And that is what's going to give us a headache. Okay, when there's one central process, things are easy to understand. When we want to reach agreement with everybody talking to everybody, it's tricky. Okay, so let's go and look at this. So the problem is that we didn't achieve consensus, that this is what we wanted to happen, but before this message could get sent, number 1 died. Okay, so now we can see that we don't have consensus. Okay, 1 guy's pending, 3 guys, the consensus value is different at the sites, and this is the problem we want to overcome eventually. Okay, so before we do that, we'll try to do the simpler problem. Okay, so we have inconsistency. And the problem is that the new sequencer may be arbitrarily behind. Okay, so we can't just say it's just one message behind. Okay, who knows what's happening? How many messages got lost? Maybe they were all sitting in that leading general's computer for retransmission. But we know that correct state is with at least one other member, and this member may die. Okay, here's another problem. Yeah, we say it's with other members, but they may also die in the middle of switchover. Okay, so you know you can't. I mean, and some algorithms say, okay, there's only one pending message, and you can't have two failures at the same time. Lightning can't strike multiple times. Okay, so we can make these assumptions and come up with algorithms, but the algorithm I will show you makes none of these assumptions. Okay, which is what's really neat about it. Okay, so what we could do is we could use the voice of multiple members, not just one member. And the key is that as long as the majority of members are around who know the information, as long as then we are fine. Okay, otherwise we are indeed in trouble. And what we will do is we'll see what we'll do. So let's go and do the simpler problem. They're assuming, you know, there was no partially committed orders. Okay, assuming all the slaves are in the same state. We just want a new coordinator, that's all. How hard is this problem?
Not that hard if you maintain your previous coordinators' stats, like what the members alive.
Yeah, we can assume that everyone knows everyone else. Okay? Let's assume that. We kind of have to assume that if anyone can take over. Okay? So how do we decide who should be the next person, next coordinator? That seems like a consensus problem. Right? We have a coordinator to make the consensus problem easier, and now we have a consensus problem in which we have to decide who the next coordinator is. So we seem to be in an infinite recursion here.
I wonder if you could do whatever client was closest to the server, so whoever had the shortest send time, so that whenever the server's back up, you can send information more quickly.
Okay, so you're saying, assuming we can decide on a common new coordinator, for some reason that process was not a coordinator earlier, so we might want to go back to the previous process. So let's make it near the other one so that in case there's some messages have to be exchanged between the two, they'll be efficient. Okay, yeah.
My first thought is to have the connection with the server in a black box to begin with, so that when one goes down, the clients don't have to do anything special other than trying to reconnect. And someone in that black box in the server takes the place.
Yeah, so there would be like a pool of servers that would come up when one of them fails. Like it will be idle servers that could be pulled up from the pool when the currently active goes down.
Okay, so what you're saying is that there's a pool of servers. What he's saying is that let's assume it happens by magic, right? There's a black box, and
that's how the clients see connecting with the server. So they don't know the difference, other than it's not communicating. But what you're saying.
No, but let's continue with your argument first. How do I figure out who to contact? You know, so how did they all decide?
That was where I was going. Like you wouldn't want to poll servers because then you have more consensus problems. That's why you want only one thing to like make up, you know, the mind of the black box is who's taking the place of the server.
Yeah.
I don't know who's in charge of it. You know,
Right.
first idea.
But can we do this black box that you're talking about that'll tell you who the next server is without having centralization?
I don't know.
So that's the key, right? Because if we have to go to a server to figure that out, then we've got another recursive problem. And what you're saying is there's a pool of servers, but as Ramon mentioned, then that leads to another consensus problem. Which one from the pool? Okay.
You could have like one of the first things that the original server would send out is who's next in line.
Okay.
So have like a list maybe 10 or 20 deep, and so everyone would go to just check the next one, and if it's alive.
It's before they all come up, there's a chain of command established. And everybody knows who the next is, the vice president now, right? So we can just have sequence numbers, and they may be given sequence numbers in that order. Okay, so this is a consensus problem. So each client A and pair should agree on the same central process. Okay, because we want only one central process. So if A thinks it's C and B thinks it's D, then C must be D. So now what we would like is one of two choices. Either we have a non-centralized algorithm that will help us choose the server. Okay, so what I will describe to you is a non-centralized algorithm, and the question is, when is that algorithm useful? That non-centralized algorithm is useful for the centralized case when the central guy fails. Okay, that's why how the recursion ends. Okay, you switch to a different system now, and that non-centralized algorithm is going to be very inefficient compared to the centralized algorithm. So we don't want to use it all the time. So we might use it only for failure case. Okay, so in fact that's one of the advertised applications of this. Or we can just and that algorithm I'll show you has 3 phases. Or we could use a 0-phase algorithm where we have a chain of command and just go to the next. Okay. So order the replicas by ID and pick the next one. And in fact, the code that I've written does exactly that. It doesn't require much code. Okay. You say, okay, if the application has not hardwired a server name, okay, if they've hardwired a server name, then I'm not going to do anything crazy or take my own initiative. I'll go and look at who the members are and pick this first element in that set. Okay, this is exactly the algorithm that I've implemented. Okay. But again, if sorted list is not sufficient, if things change dynamically, one computer becomes more lightly loaded than others, then you will need a more fancy algorithm. Okay, and just to show you this working, I put a breakpoint in the send learn notification in the central server. Okay, and then I killed it. So proposal 1, that send learn notification was sent when there was a concurrency conflict. So proposal 1 comes in, requests go out to the world. Proposal 2 comes in, it's pending, and since it's pending, it's trying to go and send back a notification saying, sorry, concurrency control problem, but it dies. Okay, and this is where it dies. And I've not figured out why I get always 2 of these messages. But this is proposal 2. It sent its request, and it never got the service denial, but it got a message that the central server died. Okay, because we've got a handler that goes and figures that out. Which, whenever peer dies, you can figure out which the peer was, and you can figure out whether the peer was a central server or not. So it gets back from the system, consensus system, the central server died, and it says, okay, I'll just keep resuming, I'll just repropose. So remember, we were reproposing, so it just reproposes, and it finds out that it's the central guy. It's getting its own messages. Okay, so this time there is no concurrency control problem. The first proposal is lost, but you get service denial for the reasons we talked about earlier. Okay, because acceptor 4 doesn't like the value. Okay.
So the 42 is never set?
42 is lost. We were the server was in the middle of getting accept responses. Okay. So acceptor 3, for instance, had sent 42, but it was never received. It had said that it's successful, that I'm fine with 42. It was never received. And when it receives the other proposal, it says success, but it got service denial. And again, number 4 had sent both these messages, but they never got received by the central guy. Okay, so it's just making things a little bit more real. Okay. So again, a non-centralized algorithm is needed if sorted list is not sufficient. And a bigger problem here is that we can have different consensus states. I didn't show that in my example because I would have had to put breakpoint down in the multicasting code. But we want to avoid this problem also. Okay? And the key was that we can use the voice of more than one member. And we said if we use only one member, that member might die. So we want to use the voice of multiple members, and we want to go from